Hey folks, how's it going? In this video we're going to go over one long worked example to show you how to do problems involving Young's double slit experiment. Now if you haven't already done so, check out my theory videos covering interference of light, path difference order number and wavelength, as watching these videos will help you apply what you learned to this video. So let's get started. Question 1a says the photoelectric effect provides evidence for the particle model of light. How does interference contradict this idea? Well, remember, interference is evidence for the wave model of light, and that provides the contradiction, which is the whole point of wave-particle duality. Part B says sketch the setup for Young's double slit experiment. Label the following on your diagram. So we want two slits, S1 and S2, a grating spacing labelled little d, that's the distance between the two slits, angle to the maximum theta, that's the angle from the centre to the point that you're interested in, the distance from the slits to the screen we're going to label capital D, fringe spacing is delta x, that's the distance between the fringes on the screen, and then we've got the first order maximum m equals 1 and the zero order maximum m equals 0. Well, starting on the left hand side we have our slits S1 and S2, and we can label the distance between the centres of the two slits as the grating spacing little d. We can then draw our screen on the right hand side and a line joining up the slits to the screen. And that's our distance from the slits to the screen, which we can label capital D. We then have our zero order maximum here, which is m equals 0, and let's draw a first order maximum m equals 1 up here. And drawing a line from the middle of the slits to the first order maximum will let us label the angle to the maximum theta. And then we can label the distance between these two adjacent fringes as the fringe spacing delta x. Lastly, I'm going to show the distances travelled by the waves from S1 to the first order maximum and from S2 to the first order maximum. So from S1 to m equals 1 we have this line here, and from S2 to m equals 1 we have this line here. So you can see we've got a non-zero path difference where the waves travelling from S2 are travelling a greater distance than those from S1. Part C says to write down the relationship concerning grating spacing, angle to the maximum, order number and wavelength for diffraction gratings. Well, this is simply just the grating equation d sine theta equals m lambda. Part D then says use the above relationship along with your sketch in Part B to derive an expression for fringe spacing delta x in terms of lowercase d, capital D and lambda. Well, we're going to be using triangles here, so we can say from the triangle above, which looking at the diagram is this triangle in the middle, we can come up with an expression for tan theta first of all. So we can say that tan theta equals opposite over adjacent. So tan theta equals delta x over capital D. So we have tan theta equals opposite over adjacent equals delta x over capital D. And we can say that for small angles of theta, we have something called the small angle approximation. So we can say that tan theta is approximately equal to sine theta when theta is a small angle. And you can try this for yourself in your calculator. For example, if you do tan of theta in your calculator and sine of theta in your calculator, you should get roughly 0.052 for both values. And this means we can rewrite this first expression as sine theta is equal to delta x over d. And we'll label this equation 1 because we're going to come back and use it later on. But from part C, we said that the grating equation was d sine theta equals m lambda, and if we rearrange this for sine theta, we can divide both sides by d to get m lambda over d. And this means we have a second equation for sine theta, which we can label number 2. So because we have two expressions for sine theta, we can say equating our two expressions for sine theta 1 and 2, we have that delta x over capital D is equal to m lambda over lowercase d. And remember, the whole point of this question is that we want to find an expression for delta x. So let's multiply both sides by capital D to get it over to this other side. So that gives us delta x equals m lambda capital D over lowercase d. And therefore we can simplify this to delta x equals lambda capital D over little d, since m equals 1 in this example. Lastly, part E says what effect do the following have on the fringe spacing delta x? Justify your answers. Part 1 says increasing the distance between the slits in the screen D. Well, from this equation that we just derived, we have delta x is directly proportional to D. So as the distance between the slits in the screen capital D increases, we say the fringe spacing should increase as well. For part 2, what effect does decreasing the grating spacing little d have on the fringe spacing delta x? Well, if we look at delta x and little d this time, they are inversely proportional. So we can say that delta x is inversely proportional to little d or directly proportional to 1 over d. So as little d, the grating spacing, otherwise known as the slit separation, decreases, delta x should increase. And lastly, part 3, using light of a shorter wavelength lambda. Well, if we look at how lambda and delta x are related, they are directly proportional. So we have here that delta x is directly proportional to lambda, so as lambda decreases for the shorter wavelength, delta x must also decrease. So where delta x increases, that would show your fringes more spaced out, and where delta x decreases, that would show your fringes closer together. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.